faces. Welcome. Welcome and goodbye, as they say. So with that, Matthias, please.
Yeah, thank you very much for the introduction, Nicolas, and also many thanks for inviting me and for all the great conversations I've had all day. It was lots of fun so far. Can you hear me properly? Does it work? Okay, great. Yeah, as I said, I'm at Uber AI, which is Uber's research lab, and we do all kind of work, essentially from computer vision to conv AI, conversational AI, all the way to reinforcement learning, Bayesian optimization, probabilistic modeling. Yes? Sorry, increase the volume.
I don't think that you can increase, only if you speak louder.
Louder?
Yes.
Like this? Okay. So essentially we do all kind of research that from deep reinforcement learning, probabilistic modeling to Bayes opt. And today we're going to talk about Bayes optimization for high-dimensional expensive functions. I'll explain in a minute what this is. Let me first acknowledge my collaborators. So in the top row, Alex Montiano, who was a PhD student in Dortmund in Germany, has now graduated as a postdoc there. And Amiable, who was my PhD student in Arizona. Bottom row is my team at Uber, David Erickson, Jake Gardner, Ryan Turner, and our intern from Warwick University, Michael Pierce, who did a lot of great work. After her talk, I will start with an introduction to Bayes opt, motivation, why we care about this. Then I'll give you a tutorial about how Bayes optimization works, what the two main components, Gaussian process regression and the acquisition function are. And then I'll talk about high-dimensional Bayes optimization, some recent work I've been doing in this area. Let me start with the introduction. What's the problem setting? So the goal is we want to find an optimizer of an expensive black box function. So we're going to find a specification of a complex design X, which is specified by usually up to 20 parameters in Bayes opt. And this objective function G is continuous and multimodal, which means it's a smooth function, Lipschitz, has multiple local optima. We want to find a global optimum. It's a black box, which means we can evaluate G of X, and we only get the function value. So we do not get any gradient, no information like that. And it's expensive to evaluate, which means every function evaluation, every given G of X takes at least 30 seconds, in many cases a few minutes, but sometimes, for example, material science or aerospace engineering can take days to weeks to evaluate one design. Okay, let me give you an example. One example is actually design of aerodynamic structures. So here a design could be the geometry of an airfoil, and the performance is then something like some combination of drag, lift, failure criteria, and so on. In order to find an optimal design under this black box objective function. So when you evaluate one design, you get an output or a collection of outputs which tells you how good this design is. So I've identified these three questions, which are what I call the Bayes optimization lens, which is our perspective in Bayes opt on such an optimization problem. So the first question is, what is the experimental decision, which means which parameters do you have to specify to actually conduct an experiment? This could be like a geometry, and so you have a couple of parameters, like coordinates of the mesh, maybe something like the structure, curvature, things like that. And for each of these parameters, you have a certain search range, so an interval of feasible values, and that gives you a search space. Okay, that's the experimental decision. The second item is the observation. Suppose you conduct an experiment, you evaluate this design in a wind tunnel or in a CFD simulation. What do you get back? What's your observation? In general, this would be a vector, right? But for today, let's just suppose it's a scalar value. And the last question is actually the implementation decision. So you're doing all these experiments, you're doing all these observations for a certain purpose. You want to find an optimal design. The question, of course, optimal under what objective function. So this is the objective function that we want to optimize. And in general, in Bayes opt, we suppose this objective function is not known in a closed form, right? There's no analytical form. It's more like the output of a simulator or a real-world experiment. Any questions so far on the Bayes opt lens? Let's do another example. Deep learning. So basically, such a neural network has lots of parameters, particularly all the weights. But these weights are easy to train, right? You can train these via backpropagation using SGD or Adam. But there are certain parameters, certain hyperparameters of the training process that cannot be tuned this way, cannot be trained this way. For example, the parameters of the optimizer itself. So what's the mini batch size, number of epochs, what's the learning rate you use during the training process, where is the learning rate schedule, dropout rate, all these kind of hyperparameters are not optimized using backpropagation, but you have to fix them externally with the hyperparameters. And Bayesopt is good for these kind of hyperparameters. Particularly, we see that if we set these parameters right, we get a substantial improvement in terms of test performance. We can use Bayesopt to set them right. So essentially what we do is experimental decision will be choose a value for the learning rate, choose a mini batch size, and so on and so on and so on. Then we train this neural network, which can take up to a week. And then we get an observation back. Observation might be the test error, for example. Okay, and we repeat this process until we find an optimal configuration. Second example, calibration of a simulator. Suppose you have some real-world data, say from a traffic simulation. You have a traffic simulator. The question is, can you calibrate your simulator to the real world? If there was like optimizing or minimizing the difference between the real world and simulation output, right? So essentially you can try different settings for your simulator, run the simulator, which might be expensive, it's complex, and in the end compare what was simulation output, what was the actual observed real world data, and you can make this difference as small as possible. Make sense? Okay. Last example, the topic I've particularly been very interested in for the last couple of years. I started work on this while I was at Cornell. Is materials discovery, material science. So here we're looking at a perovskite are next generation solar cell materials. In general, it's like a crystal which we find by some kind of central atom, and some kind of halides, cations, a solvent or a solvent blend, and other processing conditions. And again, our goal is to find the best setup, the best choice for each of these categorical variables in order to find the best perovskite, which might mean best power conversion efficiency or something like that. And here the problem is particular, we have this large combinatorial space, and you want to find the best solution, and experiments are expensive, right? It might be sending a grad student to the lab, or running some kind of DFT computation, MD simulation, or maybe a combination of those. Homework for you. Pick your favorite optimization problem and analyze it using a Bayesopt lens. See if it fits. And if you think the problem is interesting, and if it fits, then let me know. And I'm happy to chat more about this and see if there's an opportunity to use Bayesopt for your problem. So I did this in Arizona, and it turns out lots of problems actually fit this. The traffic simulation was one thing students worked on, but also optimizing the SC was another project. So actually lots of problems which can be cast in the setting. Okay, the components of Bayesopt. First component is some kind of probabilistic model. We also call this a surrogate. And this essentially gives an estimate for each point, or for each x gives an estimate of g of x, plus an uncertainty quantification of this estimate. Essentially, how confident is the model that of the value of g of x? In this example, you've seen if we evaluate the function at 4 points in total, and we see the estimates are the solid line, and the uncertainty quantification is this dashed area. And we see in areas where we have seen lots of samples, the uncertainty is rather small. In areas where we have seen few samples, the uncertainty is large. And this is done via Bayes theorem data, and we'll talk about this a little bit more later. The second component is actually the acquisition function. So given such a probabilistic model, where should we sample in order to find a global optimizer? And the acquisition function essentially uses these estimates, but also particularly uncertainty estimates, to find a global optimizer. And think of it like this: when you have uncertainty estimates, you can make sure that you do not overlook any good solution. right? Because you can make sure you reduce the uncertainty everywhere to identify a global optimum. Let me summarize the generic BGO algorithm, generic Bayesian optimization algorithm. So we start off by taking some random data. We fit our surrogate model, fit our probabilistic model. Then we go in optimization phase until the stopping criteria is met, which usually means until we have no more samples left. We decide where to sample next. We update the surrogate with new observation, and we iterate until we run out of samples. In the end, we recommend a point with best estimated value. And we use the most recent posterior distribution, the most recent surrogate model for that. Question for you, why should I use the point with the best estimated value and not the best observed value? Any ideas? When can the best observed value be misleading?
When you have a bad surrogate model.
Sorry?
When you have a bad surrogate model.
We have a bad surrogate model, but then the observation still is what you have seen. Because this comes from a function directly. Now, in practice, it's often the case that actually functions are noisy, right? So there's lots of observational noise. And if you only trust the observed value, don't correct for the noise, then you might actually you might be overconfident, you might pick the wrong point. And this actually happens often in practice, that's why I want to bring it up. So it's something to be really careful about. Let me give you an example how such a BO algorithm works. So we have seen 4 points. We have our estimate, which is the black line, and we have the shaded area, which is the confidence interval, or the uncertainty estimate. As opposed, we want to minimize. Then the common strategy is we should sample at that point which has the largest expected improvement. With expectation offers the largest improvement. And so if we plot this acquisition function, we see that the largest expected improvement is over here, which is not surprising because the estimate is low, which is great for a minimization problem. And also there's uncertainty, which means there's headroom, right? So I make a sample, I sample this point, and I was unlucky. My surrogate was bad, as you said, and essentially I sample over here. So I update my posterior, I recompute the acquisition function, and now I sample over here, where again the mean is low, and there's some uncertainty, there's some headroom, finding a better solution. I sample there, and voila, this time I found a better solution. Okay? Again, I've updated my posterior, I recompute the acquisition function, sample over here, and so on, iterate this process until I run out of samples. Okay? That's like general BGO algorithm, it's an iterative process. Setting up posterior distribution, setting up the surrogate, deciding where to sample, make the observation, update the surrogate, decide where to sample, update the surrogate, and so on. Let me talk a bit more about the surrogate before I talk about the acquisition function itself. So what does a good surrogate do for us? It somehow allows us to capture our belief what this unknown objective function looks like. Right? It's a black box, we only have seen it at a few points, potentially with noise. So a good surrogate must be able to take all this information and convert it into an estimate. However, there must be certain regularizations, otherwise the problem is intractable. If the function can jump around arbitrarily, I have no chance of ever learning this function. So general assumption is that the function is somehow smooth, right? It's somehow Lipschitz. That's the only hope that we have. If the function looks flat everywhere and has one spike, we have no chance of finding maximum ever by just sampling, right? So we need some kind of smoothness assumption to make this problem tractable. The second more important question is also, as we collect data, how can we update our surrogate? We must want to do this computationally efficiently. It should be tractable computation. And it turns out, Gaussian posed question allows exactly this. And the last question, which I'm not going to talk about today, but it's something I want to point out, is that we can incorporate prior beliefs into these models. If we know something about periodicity or trends in our objective function, we can incorporate those into Gaussian post regression, and therefore we get more sample efficiency. Okay? Let me that's one of my, I think, 2 mathematical slides that can define what a GP prior is. So again, in the Bayesian setting, we don't know what the unknown function looks like. So we model this uncertainty by distribution over functions. It's called a prior distribution over functions. And we say a prior P of an unknown function G is a GP prior with mean function mu0 and covariance function or kernel sigma 0 if for any given fixed set of points x and x prime, g of x and g of x prime have a joint multivariate normal distribution. And the means are given by evaluating the mean function at these points, and the covariance function is given by evaluating essentially the points. And the nice thing is, if I suppose Gaussian observational noise, then actually the posterior is also multivariate normal. It's again a GP. And I can compute this analytically in cubic time. So it's actually computationally tractable. I can update the surrogate at moderate computational cost. Let me give you an example what this looks like. So here's my perspective. In the beginning, I don't know anything about the function. Like any function is possible. Anything is possible. There are smooth functions, but the function can go anywhere. Now I make an observation, and all of a sudden, only certain functions are consistent with the observation I just made. Right? Only a function actually run through this point that I've observed are possible realizations of this unknown function. I make another observation which rules out all the functions that took different values in this point, and now only the smaller area, the smaller set of functions is consistent with the data. Right? So essentially I see the functions are much more constrained in their variability. I make another observation, and now the possible functions that match that match my observations are again much smaller, and they're particularly due to the smoothness assumptions. They take very similar values in these areas over here. So I can keep doing this as I make more and more observations. The possible realizations of these unknown functions are more and more confined, which is intuitive, right? I learn more about the function with every data point, so my belief gets more accurate, and the possible functions that are consistent with the data are more or less known. There's a different perspective which I showed before, which is this perspective of sausages, where we have these points in the shaded areas. I would like to convince you quickly that these 2 perspectives are equivalent. So in the beginning, where I don't know anything about the function, where every function realization is possible, this means like I have a large shaded area, large uncertainty. And now as I make an observation, what will this side over here look like? What will the shaded area look like? Any intuition?
Similar to the functions.
Sorry?
Similar to like the range.
Yes, exactly. It will be something like here the shaded area is very small, but here the shaded area grows. Exactly. So it looks something like this. So 2 perspectives are equivalent, right? This is like lots of uncertainty about the function value itself, which means there are many possible functions which are consistent with data. It's 2 different ways of looking at the same data set, the same problem. Again, to take the second observation, what you expect, well, the same thing, right? You expect some uncertainty over here, uncertainty shrinks, grows again, shrinks, grows again. It looks up like this. Okay. And I keep doing this, and I see basically what we call these sausage plots, because they look like sausages in a link. So the sausage plots are essentially the same as looking at this problem as potential functions in the distribution. Okay, if there would be observational noise, what would change? It's a small detail, but just for...
The variance doesn't go to 0.
Exactly, perfect, thanks, Ryan. Yeah, the uncertainty doesn't drop anymore to 0, because even at these observed points, some uncertainty remains, right? The observation I got was inaccurate. The uncertainty doesn't drop to 0. Some uncertainty remains. So we'd have some small shaded area at the points themselves. Okay. Any questions on this perspective of a distribution over functions? Then let me summarize. So essentially, this Gaussian process regression is a practical approach to express our belief over unknown functions. So we say we don't know the function itself, but we can capture this by a distribution over functions. And as we get more and more samples, more and more observations, this distribution becomes essentially more accurate, right? Because the mass is more concentrated on a smaller set of functions. I pointed out this inference can be done analytically in cubic time, which is okay, right? So remember that the function is expensive, so usually we don't have much data anyway, so we can afford cubic time. I'd also like to point out for larger data sets, my team is developing new techniques that use GPU acceleration, and now we can actually do GP regression up to 10 million data points. So Jake Gardner from my team is leading this. He's developing this GPyTorch package. So cubic time is still the right asymptotic complexity, but using GPU acceleration and some numerical tricks, they can actually scale up Gaussian process regression to 10 million data points and more. So exact inference. Okay, this was our Gaussian process model, our surrogate. Now let's decide, let's talk about how do we decide where to sample in each step. Okay. Recall we're acting in a world where we are uncertain about the objective function. So suppose you pick a design, you see a good value, you face essentially a decision, should you sample the neighborhood? Hopefully you can improve that already good solution to an even better solution. Or should you look completely somewhere else where there might be much better solutions? Right, that's what we call exploration versus exploitation. Okay, let me just do this. Like this. Yeah. So this is what we call exploration versus exploitation. And that's a problem every Bayes-opt algorithm faces. Exploration means we want to explore the whole search space because there might be much better solutions in areas where uncertainty is large. Exploitation, on the other hand, means we should sample the proximity of good solutions, hoping that we can improve an already good solution to a better solution. And that's a classic dilemma. Basically, whenever we act in such an environment where the function is not known, we are facing this dilemma. And one problem is that Bayes-opt algorithms act myopically. So we don't really plan ahead for multiple steps because that becomes computationally very expensive. So then you try to make a decision which somehow is good for the next step. And we hope that many of these locally greedy decisions afterwards lead to a good solution overall. Okay? And here, I think a useful strategy is Thompson sampling, which was already proposed a long time ago, 1933, but now is currently very popular again. And here the idea essentially is to say, let's sample a point according to probability that this point is optimal. It's a nice idea, but at first glance not really clear how to do this, right? Because I don't know the probability the point is optimal. So we face a problem. Basically, Thompson had a great idea, but it doesn't seem very practical at first glance. However, there's actually a practical implementation which uses this perspective we've just discovered. So recall that we have a distribution of functions over the unknown function. So what we can do is we can take a realization from this distribution. We can take one possible realization of this function, and we can find an optimum of this one realization. And we can sample there. Okay? And that's computationally very lightweight. Let me show you how this works. So here the black function is actually two unknown functions. We don't know the black function. We have not seen any data yet, so we already know the estimate is flat, the uncertainty is very large. And we pick one realization in this, of this distribution. This is one realization of our surrogate. So we can find an optimizer, an optimum of this realization, which is here. So we sample this point, and we observe this value. Okay? So we update our posterior. Now the estimate is revised. The uncertainty quantification is revised. We pick another realization of this unknown function. This realization goes to this point, because we observed we supposed there was no noise. Now again we find an optimizer. Turns out the optimizer is over here. This is the best point under this realization. So I sample this point and I observe this value. I update my posterior. Again, I draw a realization, one possible function from this distribution over functions which are consistent with my data. I look for an optimizer. Turns out the optimizer is here. So I sample the point and I get this value. I update, draw another realization. The optimum is here. I sample this point. Oh, that's really a good point. Again, next realization, find an optimizer, sample here. Okay, actually very close. Next realization, optimum is here. So we sample, next realization, and voila, I found my global optimum. Okay, so it's a very lightweight approach. We draw possible realizations, find an optimizer of this realization, and sample there. Expert question: how does Thompson sampling trade off exploration and exploitation? Any ideas? How does Thompson sampling make sure? I mean, it's easy to see how Thompson sampling samples good areas, right? Good areas are something where the realization likely has a high value, so definitely sample these areas. But how does Thompson sampling actually sample areas which have large uncertainty? Why should it ever sample there? What do we know about the realization? This realization we draw from the posterior. In an area where the uncertainty is large. We don't know anything, right? It can essentially be any value. Particularly, it can be a very large value. That's how it trades it off. If there's an area which has large uncertainty, then this realization might take a very large value there, because it's essentially not constrained. It's lots of uncertainty. And then we would sample there and thereby reduce the uncertainty. So essentially that's how the trade-off is implicit in this case. Okay, let me conclude that by showing this performance plots where we actually compare Thompson sampling to many Bayes-off packages which are out there. And it turns out that Thompson sampling performs best. This is an average plot over 50 scikit-learn benchmarks. And we see that Thompson sampling has a very good performance, despite the fact it's a very simple, trivial to implement algorithm. I would also like to point out that Thompson sampling can be parallelized very easily. Something we had in several discussions today. Suppose I want to choose, say, 50 points or 100 points at once for the next round of evaluations. I want to create a batch of points that are going to be evaluated simultaneously. How can I do this? Well, an easy way to do this is just to draw 100 realizations. And I compute 100 points, 100 optima, and I put them all in my batch. And as long as the uncertainty is large enough, these realizations will look very differently, and the points will be spread out. So it's a very simple approach. The nice thing is actually that it works very well in practice. So if you look at this, you see different batch sizes, 1, 4, and 8. This is the number of batches. This is on the x-axis, so they all take the same number of samples in total. Just basically, the larger batch size needs fewer steps, and we see that they all give more or less same quality of solution. So essentially what you get with batch Thompson sampling is you get a speed up in wall clock time. You are 8 times faster in wall clock time because you parallelize the function iterations, but you don't have to compromise in terms of solution quality. That's our empirical observation. Okay, let me also point out this type of parallelization is very cheap, right? I mean, if I take 10 realizations or 100 realizations or 1,000 realizations, that scales linearly. So it's actually very cheap to go to large batch sizes, whereas other Bayesian algorithms, other batch Bayesian algorithms usually require solving a hard problem whose dimension equals the batch size. So when you parallelize KG, for example, you have to solve a 100-dimensional problem as a subroutine, which becomes very hard. This does not become hard. So for this reason, batch Thompson sampling is computationally very cheap, and it turns out in practice to be very powerful and very efficient. Okay? Any questions? Yes.
This assumes though that you can do your evaluations in parallel, right? So if you're sending the graduate students to the lab, you can.
So all your grad students. Actually, the nice thing is, yes, it's synchronous, but it's also asynchronous. So when you get some observations terminate, some evaluation processes terminate earlier than others, and you can use the information coming back, you update your posterior, and for the new batch, basically for the new elements of the batch, you just use the revised posterior, updated posterior to draw the samples. Was it a question? Yes.
So the previous plot of different hyperparameter optimization, was that published in a paper somewhere?
No, not yet.
Okay.
A question. So, if the entropy is sufficiently large, so then this would mean that initially, when you haven't sampled a lot of points, the speed up would be, the algorithm would take advantage of the parallelization much more than.
In the end, right? In the end, when you basically have a very accurate belief where the optimum will be,
Right.
then something which is making more, basically taking the correlations between points into account will be more powerful.
Yeah.
Because in general, you want to have a batch which is negatively correlated.
Mm-hmm.
So because you want to find one good point, so if one point turns out to be bad, you want the other point to be good. So, but you don't have this here. That's the price you pay. But our empirical observation is that batch Thompson sampling works in practice very well. Okay. To summing this up, essentially we have seen GP regression is a very flexible method to build these surrogates. We learn from data. The more data we get, the more accurate our belief becomes what the unknown function looks like. We can do this inference in a tractable way, so that's fine. Batch Thompson sampling is a nice addition in order to decide where should we sample, how do we get the data. Again, the takeaway here is mostly it's very simple to implement and works well in practice. And it scales to large batch sizes. So let me use the remaining 15 minutes, 20 minutes to talk about high-dimensional Bayes-Opt. Here we make a slight twist. So far, most of work on Bayes-Opt supposes that the number of parameters you want to tune is at most 20. That's a standard Bayes-Opt setting. Then most people believe it doesn't scale beyond that, right? 20 tunable parameters, that's it. If you have more than that, well, try something else. In high-dimensional Bayes-Opt, we suppose there might be hundreds of tunable parameters. And now I'll make a distinction. If your sampling budget, number of evaluations you can take is small, then I think the best algorithm I'm aware of is this work I did at ICML this year, which I'm not going to talk about today. Feel free to chat with me about that later if you're interested in that. Essentially, it makes an assumption that the search space is in fact low-dimensional. There is some kind of inherent active subspace. And then we can actually get away with a small sampling budget. But if that's not the case, if we have a large-scale HDBO problem, we have a budget of thousands of samples, then we can actually do better. And this is a new paper with my team at Uber, scalable global optimization via local Bayesian optimization, which was just accepted yesterday to NeurIPS this year. It will be a spotlight presentation. And I will take the opportunity to talk about this work here with you, because I think I might hopefully find impactful application in your field. So let me first make a point why high-dimensional problems are hard for standard Bayes-opt. I think the first hypothesis is that a global Zoll-gate model is a bad choice for a high-dimensional problem, because a high-dimensional problem often, the nature of the function varies a lot depending on where you are in the search space. Particularly, the smoothness might change. The function might be more wiggly in some areas, less wiggly in others, and also the amount of noise in the function of evaluation, the observational noise might vary depending on where you are. And we empirically validated this hypothesis for a robot control problem, where we actually took a large number of local models, and you see when you fit the local models, you get a distribution over how wiggly how the function is in this area, how much the function varies in the area, and how big the noise is. Either no noise or some noise. But now a global GP model has to essentially choose one parameter, one value for each of these, right? It must make a call. How wiggly is the function? Because it's supposed to be a homogeneous function. How much noise is there? So a global GP model is limited in its ability to actually adapt to the function. Okay. The other thing is more technical nature. In high-dimensional problems, observations tend to be distant from each other. Keep in mind that popular kernels look like this, like the square dimensional kernel, where there is a sum over all the coordinates between 2 points. You look at the distance of these coordinates. And then if between x and x prime there's only one coordinate in which these points are far away from each other, then the sum will be large, and therefore the covariance between these points will be close to 0. Right? So these kind of exponential kernels are not a good choice when points are spread out. The second point is, well, Bayes-opt tends to spread out samples, thereby failing to identify good solutions. And why is that? We just said that Bayes-opt trades off exploration, exploitation. So if you have a 60-dimensional space, there will always be an area which has large uncertainty, and Bayes-opt will rather jump to this completely new area than following up on a already good solution. So we see that Bayes-opt is in high-dimensional spaces, it's all over the place. But it never samples anywhere densely enough to identify a really good solution. So it's a lack of focus, right? So it's a problem with the acquisition function that we have, that they don't provide enough focus for these high-dimensional problems. Let me quickly talk about the previous work that was done. Previous work always supposes we have a high-dimensional problem, but it's not really high-dimensional. So there's additive BO work, line of research, and they suppose essentially that you can somehow decompose your search space into small groups. They are all low-dimensional, and you can solve this set of low-dimensional problems one by one. And then you're golden again, because you can use your typical machinery of Bayes-opt to solve them one by one. The practice is more a problem that inferring these groups is very difficult and computationally very hard, so it can take a long time to run. But in general, that's one way of bypassing the actual problem. The other is suppose the existence of an active subspace. So you suppose that you have a 100-dimensional problem, but only 5 parameters are actually important. And so you can either try to learn which 5 the important parameters are, or use some kind of random projection and keep your fingers crossed that the random projection by chance hits the right 5. And that's also what we have done in the other paper at ICML earlier this year. Okay, we take a different approach now. So our algorithm, we call it trust region Bayes-opt, the turbo algorithm. It says, okay, let's not try to fit a global model, because we have seen, our hypothesis, the global model is a bad choice for a high-dimensional problem, which looks very different in different areas of the search space. So let's rather take a locally constrained model and we fit this to this area using its observations. So at least in this area where the model is centered, it is a good fit. Okay, and then do batch Thompson sampling, because batch Thompson sampling we saw is cheap and performs well. That's fine. We give some multiple that this is cheap. Particularly, it's our only condition on the samples observations taking as part of this trust region. The number of samples used in the inference is rather small, so the computation cost stays cheap. But now my intuition is that this trust regions actually perform a local search. So what we do is actually we have this local model. Inside the local model, we do Thompson sampling, which means like we're taking new observations, and whenever we have found a better solution, we move the trust region to the better solution. And basically now the trust region starts moving around in this high-dimensional space, hopefully moves towards some local optimum. And if the model provides better solutions, we can grow the trust region. If the model provides no good solutions, we shrink it. And eventually, if we don't make any progress, then we just essentially discard the trust region and start somewhere else. So it's like a local search approach, where we have these local searches that walk around in this high-dimensional space till they reach some local optimum, and then we start somewhere else. Okay? And the nice thing is because we sample only inside the trust region, we are more exploitative. So the samples are confined to this area where we believe the model is good. So actually we are focusing on this area where we're currently at and trying to make progress there rather than spreading things out all over the place. Let me also show you examples. So here's this a contour plot of the unknown function. We have a global optimum here, a global optimum here, a global optimum here. And you see essentially the contour plot, the function differs quite a bit depending on where you are. So we have taken a couple of samples. Our current trust region looks something like this. So when you compare the model, you see now the green lines are essentially our GP model. These are the contour plot. This is the contour plot of our GP model. This is the contour plot of the actual function. And you see it's doing an okay job inside the trust region. That's okay-ish. But it's definitely bad over here. Right? Basically, the trust region's model is completely inaccurate outside the trust region. That's fine with us. I mean, we focus on this area, and inside the trust region, we're doing okay. So we take a couple of samples and we move the trust region around. And in the end, after a couple of samples, we have sampled very, very densely around the global optimum. And we see that now, by putting on top of each other the contour plot of the GP model and the contour plot of the actual functions, we see that they actually are a very good match in this area. So basically, we have achieved the goal of having a model which is locally fit well. And the trust region has moved from here closer to the optimal solution. Okay, so it's like an iterative process, a sequential search. That's fine. So what this currently looks like is something where I start my local search somewhere, it walks around, hits the local optimum, so I start from scratch somewhere else randomly, walk around until the local optimum. If I keep doing this forever, I'll probably have a good chance of finding a global optimum sometime, right? If I hit the right Bayesian of attraction, I'll find a global optimum, but this is definitely not efficient. Right? Why should I essentially keep a local search alive if it has little promise of giving me a better solution than I already know? That gives rise to our second key idea. So can we be more efficient than just having sequential local searches? And the answer is yes. Let's have several trust regions. So you have several trust regions. They're instantiated randomly all over the place. And now I do Thompson sampling for all trust regions simultaneously. And what this means is that as we allocate samples, promising trust regions will receive more observations, will receive more samples, than trust regions which are somehow stuck in an uninteresting corner. Okay? So literally what I do is I take a Thompson sampling from each trust region, I pick the best among all M trust regions, and I add this one to my batch. The others I discard. And this is a way which favors trust regions which are in promising areas. So essentially I get an imbalanced sample allocation which favors promising trust regions. Okay? So summing up the turbo algorithm, we have the setup phase. Contrast this with the standard VGO algorithm I showed earlier. In the beginning, we set up our model by randomly creating points, picking the best as a center for our trust region, fitting the GP model as before, and then we step in our optimization phase. And then to create a batch of size Q, we create a Thompson sampling in each trust region, but we only keep the best out of these M points and add it to the batch. And we iterate this a few times, and then we evaluate the batch, we update the posterior, the new observations, we update our GP models, and then we update the trust regions, meaning we grow trust regions that performed well, we shrink those who underperformed, and we replace those essentially have for a long time failed to produce anything useful. And we repeat this process, and in the end, we recommend the best point as usual. Okay? Let me show you, quickly point out the baselines that we have out there. There's the Bohemian algorithm, which combines Bayesian with neural networks, which is scalable. There's our Hasbro algorithm from ICML earlier this year. But we also compare to stochastic optimization algorithms, particularly the genetic algorithm CMES, which performs very well, Cobaila, which is a trust region method with a polynomial model, which comes from the operations research community. Okay, let me show you some experimental results. The first is a 40-dimensional robot control problem. Turns out it has sparse rewards. So the search space looks flat in many areas. There are only certain areas where actually something happening. So definitely it's a heterogeneous function where a local model is advantageous. And indeed we see that our algorithms, the turbo algorithm, with one trust region, with 30 trust regions, outperform the rest by quite a bit. Particularly other algorithms seem to plateau here, whereas turbo still makes progress. Also we see that having multiple trust regions, which is the black line, does better than having only one trust region. So for the same number of samples, same number of evaluations, we get a significantly better solution. So basically this kind of imbalanced allocation of samples really pays off. Okay. Second is the robot trajectory planning problem, 6-dimensional trajectory planning problem. We have to choose 13 waypoints in 2-dimensional space. And again, we see our algorithms outperform the others significantly. In the interest of time, let me skip these RL problems. Let me also point out, we run this on a 200-dimensional synthetic benchmark. Again, we perform better than the other algorithms. My question for you, if you have suitable problems which are high-dimensional, expensive functions, and would like to test this algorithm, please let me know. I would be curious to see how the algorithm performs on other problems as well. We're currently looking for interesting problems to solve. Okay, let me summarize. I hope I've convinced you that Bayesian is a powerful method to solve expensive black box functions. Particularly we talked about GP regression, which is a flexible model to capture the uncertainty, do regression on these kind of smooth functions. And I would like to point out that Cornell, Momo, and Botorch are popular implementations that are easy to use if you have any Bayesian problems. My recommendation is to try one of these. We also talked about the turbo algorithm, which gives excellent results for high-dimensional problems. I think that's a breakthrough because the current approaches were very limited in applicability, and turbo performs much better and addresses these inherent problems that high-dimensional problems pose. Particularly, the sequence of local models seem to have a better fit than one global model, and also this imbalanced allocation gives more sample efficiency than just spreading out the samples all over the place. In this context, also based on the conversation I had earlier, I would like to point out some other work I've done in the area. The first one, multiple information sources, is some kind of multi-fidelity Bayes-opt. Particular information sources which are not hierarchical. It's not clear how these relate to each other, which happens sometimes in material science, for example. Then the MISO algorithm might be of interest for you. We've currently applied it with Paulette Clancy from Cornell, previously Cornell, on perovskites, and it worked actually quite well, having different types of DFT simulations, different level DFT simulations. Based on the gradients, sometimes you have gradient information available. For instance, if you use the adjoint method, then you should use that, right? It's free information, so you should use that to create more efficiency. Another work is actually the box algorithm based on for combinatorial structures, which I'm currently very excited about. So often we don't have a continuous space with categorical variables. Maybe you have a network or something like that, and want to make decisions based on that, find the best street network, something like that. Then the box algorithm can be applied. I think that's a very interesting research direction, and already like 3 follow-up papers in 1 year, which go down the same area. So I think that's a very promising area to work in. I'm currently interested also in black box constraint, which I also discussed with Matt very quickly today, and gray box functions. So sometimes the assumption if you have a black box function is just too restrictive, right? Sometimes you actually you get a lot more information. We can look inside the simulation. We can get maybe norms of the gradient during training or things like that. So we know much more than just the scalar value at the end. So if we can look inside the simulation, we can see maybe if it's a warehouse simulation, which items will run out of stock or something like that. If we look at a chemical simulation, we can see which part of the molecule actually connect to the surface. So we can learn much more than just say the connect time. So we should use this information. So I think gray box optimization is actually a very interesting area to work in. Okay, thanks.
So I have a question. Is it possible to use Bayesian optimization to optimize along a set of samples from the search space? Because then, if we maximize our acquisition function, there is no guarantee that that exact point is among our samples. But there's something close to it, but not exactly that. It's not basically the whole search space. It's just samples from that search space. Is it possible to do that with Bayesian optimization? Or?
So by optimizing a sequence of samples, you mean something like look ahead? When I decide the next 10 samples I want to take in some order?
No. So basically, if in Bayesian optimizations that you show, there's a function and we optimized a point from it. It's continuous. So you maximize your acquisition function and you find where you want,
Yes.
get your new observation. But imagine that we only have, for example, 100,000 samples from the basically search space, and if you find where you want to update your new observation, that exact point might not basically.
Oh, okay, I see. Yeah, actually there is some work in that area, things related to input uncertainty. So there are also settings where you say, I would like to evaluate this design X, but then for some reason what you actually have evaluated is X plus some unknown vector Y, right? And that's called input uncertainty. There's some work on that. For instance, Jürgen Pranke from the University of Warwick has done some work in this area. That's an interesting field. So people then start essentially averaging over the neighborhood in the search space. Yeah, that's an interesting field.
One more quick question. So in the trust region method that you mentioned, do you find your trust region after a few iterations, or when do you select your trust region? The initial one.
The initial one, we do some kind of space filling design, say like a hypercube design. We evaluate the expensive function at all these points, and then we pick the best point among these as the center of our first trust region. And then we can repeat this, if you want to have m-trust regions, we repeat this process m times.
And you update the basically region every few iterations, right? Or
Yeah, no, that's essentially a hyperparameter of the algorithm. You can choose how you want to make the updates. So, so currently, we say if it makes progress, we increase the size, and if it fails to make progress for a couple of samples, then we should decrease the size. And when going deeper, I think the reason that this actually works well is that we do batch acquisition. So we take several samples. So the chance that one of them actually is good is better than for just one sample. Yes.
So about the Bayesian vision gradients, how so if you use I assume the gradients are from the survey.
Here we suppose that we get actually an observation, maybe incomplete, maybe noisy, of the gradient of the unknown function. So, give an example. When you want to, the problem of maximizing the log likelihood can be expensive, right? Because the computing log likelihood can be expensive, has cubic cost. But then getting the partial derivatives only has quadratic cost. So you can actually, once you've done all the work, you can actually get the gradient cheaply. And the log likelihood is often a multimodal function. You can use Bayes-Opt gradients to do that. Essentially, you can get the gradient of the unknown function in this case. You can get the gradient of the expensive function.
So,
log
so
marginal
in
likelihood.
context of GP.
Sorry?
In context of Gaussian process.
It doesn't have, yes, it can be. So one example we looked at, for instance, is a spectral mixture kernel, where essentially, that's a technique where you suppose that the spectral density of the kernel is modeled by a mixture of Gaussians. And then you can choose the mean and the variance of these Gaussians and their weight in the mix. And these are essentially the hyperparameters you want to tune. And then you can compute the log marginal likelihood of this model that you're fitting with the spectral mixture kernel. And you compute the gradient of this log marginal likelihood. And then you can use Bayes-Opt with gradients to find a maximum of the log marginal likelihood, which hopefully is a good fit for your model. So it's not necessarily related to GPs. So it is true that what we use in a Bayes-Opt setting is that the derivative of a GP is again a GP. So we have a joint GP prior on the gradient in the function itself. But the gradient observation of the unknown function is separate from that. That comes from it depends on the use case. But we suppose at least for some parameters we can get derivative information. Does that make sense? So in some cases, basically, when you ask for g of x, you not only get g of x, but you also get the gradient at x of g. Also aerospace settings, another example for that, you can actually get that. And then you get more information every step, and therefore you can find an optimizer faster.
Yeah, so my question is, how does that compare? That using gradients to update x, and how they compare to, for example, in Thompson's sampling?
Okay, I see. Yeah, actually we have a different acquisition function. So the problem with Thompson sampling is essentially only focuses on the function value itself. So it's not straightforward how to use the gradient. So definitely incorporating the gradient information you get from the unknown function g improves your posterior because you get more information. So Thompson sampling will become better than not using it. But Thompson sampling does not account for the fact that you will observe a gradient. So what I propose in my paper is the DKG algorithm, which when it makes a decision where to sample, it is aware that the next sample will give g of x plus the gradient. And by taking into account that you also get a gradient observation, you can make even better decisions. So it's like the algorithm is aware that we'll get much more information. So it takes the uncertainty of the gradient into account as well. Because if you learn basically, if you're unsure if the gradient looks like this or like this, then it might actually be valuable information, right? Because you know afterwards whether the optimum will be here or there. Any other question? Yes.
Yeah, regarding the initial, your selection to choose the size of the trust region, I'm curious of how sensitive the actual optimization process is to that kind of heuristic initially, because I could imagine, you know, a large dimensionality, maybe one dimension is a lot more variance than several others in that case. So how exactly do you pick that first bounding box to start changing to?
Yeah, to be honest, we currently do a really lousy job at that. We currently only we initialize at a hypercube, which is size 1, it's like the whole search space.
Do you also grow the box in some dimensions?
Yeah, we don't
Or
go
you
further
don't
than that, but because we initialize it with a maximum size.
Okay.
So we can't go it further. But actually what you said is something we also thought about. We should take the length scales that we have known, that we've seen in the past into account.
Yeah.
And actually, because some dimensions might be very smooth, might be a bit larger, others might be very wiggly, might be smaller, but we don't do that yet. So we have actually lots of loose ends in the turbo algorithm of making these things better. Also the model fit, we don't really compute the model fit exactly, but we could also make a decision based on growing or shrinking based on the model fit. So we could have something like an information criteria. Yes?
So in the robot 2 example, the robot only has 2 arms, and how do you use 14 dimension to design why 14 dimension?
Actually, I have to look this up. I have to come back to you about that. I don't remember what the 14 parameters were, but I think it was something like, it's a control policy, right? We don't optimize the arms directly, it's a control policy that we tune. So it's like a parameterized policy that controls the robot arm, and we tune this policy, not the arms directly. Sorry?
Probably 7 joints per arm, something like
Yeah, maybe, I don't know.
It's not the arm.
I mean, it's actually true, many of these policy search problems, one supposes there's a kind of parameterized class of policies, and you try to find the best one. I mean, I skipped this example of the lunar lander, but there's another reinforcement learning benchmark where essentially you have to choose the policy, you don't choose the action directly. Any other question?
I think this is a good time to stop. Thank you very much for visiting us.